Welcome to the first lecture on randomized algorithms. The textbook for this course that we will be following is the textbook by Michael Mitzenmacher and Eli Upfel. The name of the book is Probability and Computing, and the second textbook for the course will be Randomized Algorithms by Motwani and Raghavan. So, before we study randomized algorithms, let us first try and understand in what way does randomization help. If we have a deterministic algorithm, one possibility is that for every deterministic algorithm, the adversary could choose a particular input which could make our algorithms perform extremely poorly. So, for such adversaries, randomization can probably help. That is, after taking the input, we are not, mind you, we are not choosing a random input, but let us say we take the input given by the adversary and modify it in a certain sense in a random way, over which the adversary has no control. So, this is possibly one way in which randomizations could help in a wide variety of computations. We will see more examples of how randomization helps, but let us first begin by looking at a randomized algorithm that all of us are very familiar with, which is the randomized quicksort. So, let me just write down what are the inputs, input and output for this algorithm. So, input we will assume is a set S of n integers. We will assume for the time being that these are distinct integers, okay. And as output we will expect the sorted version of S. So, if S was equal to A1, A2, AN, then the sorted version would be, let us say, AI1 followed by AI2, followed by AI3, followed by AI4, so on up to AIN. So, that is what we expect as the output. Now, deterministic algorithm which does this. For a randomized algorithm, let us first understand what are the requirements that our algorithms must meet. So, we could ask, let me just ask these following questions. Does the answer always have to be correct? This is a requirement. Second, if the answer to this is no, then is it that for all but a few inputs the algorithm work correctly? Think about these questions, and that will help us understand what exactly is the input output characteristics that must be satisfied by a randomized algorithm. Let me describe the randomized quicksort algorithm, and then we will again revisit these issues. So, the first step is choose a number y uniformly at random from S. Okay, so, each A1 to AN is equally likely to be chosen in this step. The second step, construct the subsets S1 containing all elements of S which are less than y, and construct the subset S2 containing all elements of H which are greater than y. And then the third step would be the recursive step. Recursively sort S1 and S2 and then output S1, that is the sorted version of S1, followed by Y, followed by S2. So, that will give us the sorted version of the set. Now, what is the randomness? How does it affect the input output characteristics of this algorithm? The only place where we are using randomness here in this algorithm is in the choice of the random element from Y. We know that for this algorithm, the answer returned will always be a sorted input. But the running time for this particular algorithm, the running time is a random variable. The running time is a random variable. Now, when we say that the running time is a random variable, does it depend on the initial set of integers, or does it depend upon the choice of y? You can see that it is just a function of the choices that we make inside the algorithm. It is not really dependent on the input integers. So, this algorithm is going to give a random running time. What we are interested in is the expected running time of this algorithm. We could also look at the probability that the algorithm fails to complete its task in a given amount of time. Okay. So, those are the kind of questions that we will be looking at when we study randomized algorithms. So, here we mentioned that the running time is a random variable and it depends only on the choices made inside the algorithm. In particular, if you look at, let us say, bubble sort, there are certain inputs on which the algorithms could do particularly bad. But here there is no input on which we can guarantee that the algorithm will do poorly. In fact, for every input, no matter what the input is, the running time is only a function of the choices that we make inside the algorithm. It depends only on the random choices that we make inside the algorithm. So, when we get the expected running time, it means on every input the expected running time is such and such, as opposed to we are not saying that for the average input the running time is such and such. We are saying for every input the running time is going to be a certain, the expected running time is going to be a certain value. So, let us do an example of this randomized quicksort. So, let us say our set of numbers is following 1, 8, 5, 3, 11, 12, 6, 97, 33. Okay. Suppose the first element that we pick is 3. Okay, so, let us say 3 is the first element that we picked. When we split this, we have one set of numbers namely 1, and everything else is greater than 1, namely 8, 5, 11, 12, 6, 97 and 33. Again this is already sorted, so nothing to be done there, single element set. From here we again choose a random element. Let us say if we had chosen 6, then this again gets split into 2 parts. 5 will be on one side, or let us say this time we will choose 11 instead of 6. So, if we chose 11, on the left side would be 5, 8, 5, 6, and on the right side will be 11, 12, 97 and 33. And let us say here we had picked 6, this gets split into 6 and 8, and here if we had picked 33, and this gets split into 12 and 97. Okay. So, this is how the algorithm works, and basically I have drawn the answer, the computation in a tree format. So, that consists of these nodes. So, if we do a in-order traversal of this tree, I will get the sorted list 1, 3, 5, 6, 8, 11, 12, 33 and 97. So, this is how the algorithm works. If we had instead of 3 chosen a different number at the start, we would have got a different tree, and depending on that tree, the running time of the algorithm could vary. What we are interested in is on the average, how much time does this algorithm take? What is the expected running time of this algorithm? We will do that analysis. Okay, so, let us introduce some random variables, but before that let us say Si denote the element in S with rank I. So, the ith smallest element in S, we will denote it by Si, and let us, so this is not a random element, this is a fixed, Si is a fixed element. If you are given a particular input, Si is the ith smallest element in S. Now, let us introduce a random variable Xij, which we will define to be 1 if Si and Sj are compared during the course of the algorithm and equals 0 otherwise. Okay. So, if we look at any particular element Si and Sj, if they are compared during the execution of the algorithm, then we will have Xij equals 1, otherwise we will have Xij equals 0. You can note that Xij equals 1 would imply that these are compared, and that is the only, I mean any element I and j are compared at most once. Certain elements may not be compared at all. So, the total number of comparisons gives us a bound on the running time of the algorithm. So, if we look at summation Xij or all I less than j, okay, this can be written as summation I going from 1 to n, summation j going from I plus 1 to n Xij. Okay. So, this is the number of comparisons. We want to estimate how much is this. So, let us see when will Xi and Xj be compared. So, here you can see that anything in the left subtree will not be compared with anything on this right subtree. For example, if you look at 11, based on 11, so all the elements below 11 were compared with 11, that is how we split it into two parts, but 6 is not going to be compared with 33, okay, because they fall in different subtrees. Similarly, 1 is not going to be compared with 11, everything got compared with 3, but they are not going to be 1 is not going to be compared with 12. Okay. So, Si we can write this fact as Si and Sj are compared if and only if Si is a parent of Sj or vice versa. Okay, if they fall in distinct subtrees, they are not going to be compared. If one element is a parent of the other, that is the only case in which they will be compared. Okay. So, now this is when Xij is equal to 1. So, let us call this number of comparisons as x. What we are interested in is, so our aim is to compute the expectation of x. By linearity of expectation, we know that this summation, this expectation is just the sum of the expectation of the individual random variable. So, we can write that expectation of x is equal to sum over say I less than j expectation of xij. Okay, and xij being an indicator random variable, its expectation is going to be just the probability of the event it indicates. So, expectation of xij is equal to 1 into probability that xij is equal to 1 plus 0 into probability that xij is equal to 0. So, this we will call this as Pij. The probability that xij is equal to 1 we will indicate it by Pij. So, therefore, expectation of x is going to be summation over I less than j Pij. Okay. Let us compute that probability, how much is Pij going to be. So, we can also write it as summation over I going from 1 to n, j going from I plus 1 to n Pij. So, let us look at the element Si and the element Sj. When will they be compared? So, there are I minus 1 elements here, in between there are certain elements, and after this there are certain elements. Now, in our algorithm we are randomly choosing various pivots. In this interval from I to j, there are precisely I minus j plus 1 elements. Okay, so, if this is the 10th element and this is the 20th element, then in between up from 10 to 20, including 10 and 20, there are 11 elements. In our algorithm, at each stage we are randomly choosing an element y, which we may call as a pivot element. So, if an element in between Si and Sj is being chosen as the pivot element before Si, then Si and Sj will not be compared. For example, let us say if this element, let us call this as alpha, if alpha was chosen before Si and Sj, then what we can say is alpha will be compared with Si, it will go into one subtree and Sj will go into another subtree, and there is no possibility of comparing Si and Sj. The only case in which they will be compared is when out of these elements, these I minus j plus 1 elements, either Si or Sj is picked before every other elements inside this. Okay. So, I will write this as a fact. Si and Sj are compared if and only if Si or Sj is chosen ahead of the elements in between Si and Sj. Okay. So, we can imagine the entire algorithm in the following way. We choose a random permutation of 1 to n that tells us the elements that we are going to pick as pivots in each stage of the algorithm. Okay. So, in amongst these permutations, we need to find out the number of permutations in which Si or Sj appears before an element in between Si and Sj. So, that happens with the probability that Si and Sj are compared is equal to, we denoted this by Pij, this is equal to 2 divided by j if you assume I to be the larger element, if you assume I to be the smaller element, then this becomes j minus I plus 1. While considering a random permutation pi, let x be the first element chosen from Si to Sj. By symmetry, each element in the set Si to Sj is equally likely to be x. But if x is anything other than Si or Sj, Si and Sj will not be compared during the sorting process. So, the probability that Si and Sj are being compared is equal to the total number of favorable choices for x, which is 2, divided by the total number of choices that we can make, which is j minus I plus 1. So, Pij becomes 2 divided by j minus I plus 1. So, therefore, summation I less than j Pij will be equal to summation I going from 1 to n, summation j going from I plus 1 to n 2 by j minus I plus 1. Okay. So, when j equals I plus 1, this quantity is summation I equals 1 to n. This will vary from k equals 2 to n 2 by k. Okay. So, this summation is at most, so this is less than, the inner summation is less than Hn. So, this part is Hn. So, we can say that the whole summation is less than I going from 1 to n Hn, where Hn is the nth harmonic number. It is equal to 1 by 1 plus 1 by 2 plus up to 1 by n. This is approximately log n. Okay. So, the overall summation is going to be less than n log n, or you can say it is approximately n log n. Okay. So, that tells us that randomization can help us come with very simple algorithms with very good running time. We will now look at yet another problem in where randomization helps us, which is the problem of matrix verifying matrix multiplication. So, let us state the problem. The input is 3 matrices we can assume that A, B, C are n cross n matrices over some suitable field. The elements come from a field F. Okay, you can think of them as real numbers. Okay. Now, what we are interested in is the output should be yes if A times B is equal to C, and this should be no otherwise. So, if the matrices A and B multiply and give us the matrix C, then the answer is yes, otherwise the answer is no. Okay. Let us think of an algorithm to do this. We could simply multiply the matrices A and B and then compare it with the matrix C. That is going to take us this multiplication. If we do a naive multiplication, we will require n cube steps, and then we can compare it with C, that is going to be taking n square steps. So, the running time of this algorithm, a deterministic algorithm, is bounded by n cube. You require no more than O n cube. Of course, we could do faster multiplications of the matrices, in which case we will get something like n raised to omega, where omega is the exponent of matrix multiplication. Okay, so let us say something like 2.5, okay, whatever is the value of omega. Okay. That is still greater than the input size. The input size is n square. There are 3 matrices of size n cross n, which means the input is of size 3n square. Okay. So, can we get an algorithm which will do this task better than, let us say, these algorithms by, I mean, instead of, can we do it without multiplying out matrices A and B? Is there some other way? Now, there is a simple technique. Okay. So, write down the algorithm, choose a vector. So, we will think of this as a n cross 1 matrix randomly. Okay. So, all possible n cross 1 matrices or vectors are equally likely. Compute, so this vector let us call it as x, compute A B x and compute C x, return yes if A B x is equal to C x, return no otherwise. Is this a better algorithm than the previous algorithm wherein we just computed A, B and C and then compared them? Well, this algorithm could give incorrect answers. There are certain inputs on which the algorithm could give incorrect answers, but there are certain inputs the algorithm will never give incorrect answers. For example, if AB is equal to C, no matter which random vector you take, you are always going to get AB, you are going to get the answer yes. Okay. But there are certain inputs on which the algorithm could give incorrect answers. Okay. For example, if AB are not equal to C, then there are certain x's that you could choose which could result in the answer yes, when the correct answer would have been no. For example, when if you have two matrices such that AB is not equal to C and the random vector that you chose was unfortunately, let us say, the all 0 vector, if you multiply that with AB you will get 0, and if you multiply it with C then also you will get 0, and 0 being equal to the 0 vector being equal to the 0 vector, the answer would be yes, whereas the correct answer would have been no. Okay. So, clearly this algorithm does not have some properties that the earlier algorithm did not have. I mean, for example, it gives incorrect answers, okay, some certain undesirable properties. But what have we gained out of this? I mean, by introducing, I mean, we now have a chance of committing mistakes. What did we gain by doing that? Well, the running time of this algorithm is much better than the previous algorithm, because here the matrix multiplication we will compute it in the following way: A times B times X. Now, B being an n cross n matrix and X being an n cross 1 matrix, the multiplication only takes O n square, okay, because we could just take the matrix, this is the matrix B, and multiply it with, so these elements are multiplied with these elements. Okay. So, that takes O n to compute one element. We have, let us say, n elements to compute, each of them can be computed in linear, I mean O n order of n time. So, total running time is O n square. So, this computation can be done in O n square, and you will get a n cross 1 matrix, which again can be multiplied with A, which is an n cross n matrix, and that also takes O n square. So, this entire computation can be done in O n square time, and then you have to compare it with, you have to compute C x and compare with it. So, the total running time is O n square. Okay. So, this computation takes only O n square time. So, we have saved on computational effort, but we have introduced errors. So, we will try and analyze how bad is the error. Okay. So, let us look at the matrix A B times X being equal to C x. This is the only case, sorry. So, if A B is not equal to C, the algorithm could return two answers. If A B is equal to C, the algorithm will always return the answer yes, and that is the correct answer. When A B is not equal to C, the correct answer should have been no, but the answer the algorithm returned could be yes. So, we want to compute the following probability that A B is not equal to C and the algorithm returns yes as the answer. So, when does this happen? So, since A B is not equal to C, we can look at the matrix A B minus C. Let us call this as the matrix D. Okay. So, the algorithm returns yes only when this D times X is not equal to this is equal to 0. We know that D is not equal to 0, but D times X is equal to 0. So, we will look at this probability that dx is equal to 0 under the condition that D is not equal to 0. Okay. So, D is this matrix which contains lot of elements, let us say D11 up to D1n, Dn1 to Dnn. Okay. So, this times x1, x2, xn is equal to 0. We want to look at what is the probability of. So, this is our matrix D, which is known to be a non-zero element, at least one of the elements inside this is a non-zero element, and we want to look at amongst the choices of x1 to xn, how many of those choices would result in making this product 0. That will basically give us a bound on the error probability. So, let us we can assume without loss of generality that D11 is the non-zero element. If D11 was not the non-zero element, we could carry out this entire analysis by shifting rows of D and columns of D to make D11 the first element, and then x1, x2, xn has to be chosen appropriately. So, let us say that D11 is non-zero. Now, if we get this entire matrix to be 0, clearly one requirement is that the first element in the column vector dx, if you consider the column vector dx, the first element inside that should be 0. That would give us this equation D11 into x1 plus D12 into x2 plus D1n into xn should be equal to 0. So, let us imagine that these choices, the choices for the random variables x1, x2, x2 up to xn. So, these random variables, let us say that their choices were already made. Okay, so that gives us some particular vector with x1 not yet being chosen. Now, once you fix these x2 to xn, this expression D12 up to D1n, they get fixed, and let us say that value is alpha. Okay. Now, we can look at this as a linear equation. D11 times x1 plus alpha equals 0. Therefore, x1 is equal to minus alpha times D11. In other words, there is precisely one value of x1 that you can choose, which will result in dx being 0. So, if the random vector was chosen in such a way that each elements xi was chosen from a field of size, let us say f, then only one choice out of mod f choices would result in the algorithm returning an incorrect answer. Okay. Even if the field was of size 2, the probability of error is less than half, because the probability of error is going to be less than 1 by size of the field, which is certainly, so this quantity is certainly less than half. Okay. So, we know that the probability that the algorithm makes a mistake is no more than half. But is that good enough? So, we will do something that we will be using again and again, which is the notion of repeated trials. Okay. So, we have an algorithm which checks if AB equals C, and it returns the correct answer with probability greater than half. Okay. So, probability of success is greater than half, or in other words probability of failure is less than half. By success, what we mean here is that the algorithm returns the correct answer. This is an algorithm which returns the correct answer every time when AB is equal to C, and it returns the correct answer with probability greater than half when AB is not equal to C. Now, let us just repeat the algorithm 100 times. Okay, and we will note down the answers returned by the algorithm. If the first time the answer is no, and the next is yes and no and so on, okay, what can we say? If AB were equal to, so we just repeated the algorithm 100 times. So, the running time is just C n square, where C is an absolute constant. Here it is, let us say we repeated it 100 times. So, 100 n square is the running time. If now, if this was the output, we know that if AB were equal to C, then the algorithm would never return the answer no, okay, because on all inputs A and B which are equal. So, if AB is equal to C, for every x, ABX is equal to CX. If AB is not equal to C, there might exist x such that AB x is not equal to Cx. Okay. So, here if the algorithm says no, that means the algorithm has found out some x such that ABX is not equal to C, right. So, even if there was one such, the answer is going to be we can conclude that AB is not equal to C. So, even in this 100 repetitions, after processing this, we will say the answer yes only if all 100 trials resulted in yes, and we will say no when all trials, I mean so we will say no otherwise. Okay. So, we could also just stop at the first time a no appears, okay, that is equivalent. Instead of doing it 100 times, we can continue doing 100 times if all the previous runs resulted in yes. Now, what is the probability of success of this algorithm? Well, each of these repetitions being independent of each other, if AB were equal to C, our algorithm will be correct with 100% probability. If AB is not equal to C, each trial the failure probability is less than half. Each trial we argued that the success probability is greater than half. Therefore, in each trial the failure probability is less than half. Therefore, for 100 trials the failure probability is less than half to the power 100. Only if each of the trials fail, we will be giving the answer no. Okay. So, therefore, this is a very small number. So, we still have an O(n) square algorithm with very small error probability, or in other words we have very high error probability, high success probability. We will stop here for today, continue our study of randomized algorithms in the next lecture.